Good afternoon and welcome to our webinar on product cannibalization. It's great to have you join us today. Let me start off by introducing our team. Myself, I'm Stefan Conradi. I'm the managing partner of Bayesian USA. And with me on the line is my colleague Stacy Blodgett, You may have already met Stacy in different contexts. You may have spoken to her on the phone. While she will not be speaking or presenting today, she's monitoring all the questions that are coming in, and she may directly respond to you with any of the questions you submit today. So today's program, we will start off with some motivation and background for our topic today. I'll talk about definitions and share with you an introductory example. After that, we will proceed to presenting Bayesian networks as a conceptual framework to capture and represent our problem domain. And with that, we will see how we can perform probabilistic reasoning. But then we really get to the main part, because then we want to see how we can learn and estimate and finally perform inference on with cannibalization data and see how we can really reason about the problem domain and ultimately establish policies or optimize policies, I should say. A central point in this context will be the whole issue of how can we perform causal reasoning, how can we perform causal inference with a machine-learned Bayesian network model. In that context, we will talk about the disjunctive cause criterion, for instance, and several other things. Now, that second part of today's presentation, that we will do, or in that second part, we will do a software demo. But I should already tell you up front, all the numbers, all the values we see, these are all fictional numbers. So I'm not going to share any trade secrets or anything. So, as always, all the slides from today, as well as the webinar recording, will be available for download either later today or over the weekend. So even if you miss parts of the presentation, you can catch up later. So let's get to our main topic. And I'm kind of starting off stating the obvious, because typically when you launch a new product, that new product adversely affects the sales of an existing product. Yeah, that's fairly straightforward. If it affects your competitor's product, we would consider it as a conquest, and that's what we usually like. However, if this new product launch affects our own products, then we would consider it as cannibalization. And that's obviously what we wish to avoid. We certainly don't want to hurt our own business with our own products. So now this whole topic is very close to my heart, since I've worked in the auto industry for many years. In fact, I was product manager of several of the products you see on this slide. And cannibalization was always a very important question for assessing the business viability of future vehicle projects. So there was always an important topic. However, cannibalization was often dealt with almost like a mysterious dark force that, like the CFO would bring up, as opposed to something that we simply have to formally quantify, estimate, and reason with. So in that sense, this topic I find that topic very interesting. And let's stay in the auto industry, go back to the year 2000, and look at a very simple introductory example of how cannibalization might happen. So in the year 2000, BMW launched its first sport utility vehicle, the X5, and that was the first such vehicle in the segment, in their product portfolio. Turned out to be quite successful. I always liked that car. And given its success and the growth of the SUV segment in general, BMW planned to introduce a second SUV, a smaller, less expensive vehicle. They named it the X3, and we're planning to launch that in 2004. So now the obvious question is, well, to what extent would the newly launched X3 take away sales from the X5? Would there be any cannibalization? Would that affect the X5? Well, what we want to do now is to think about how we can represent this as a Bayesian network and how we can formally reason about this topic. So let's create a conceptual network. Here are our two vehicles that we want to evaluate, and now we will represent their relationship in the form of a very simple Bayesian network. We have a node for the new product B that affects the existing product A. And hypothesizing about this, I would speculate that probably an increase in sales in new product B would negatively impact the existing product A. Cannibalization, that's after all the topic of today. But what I should point out is really that I consider this as a causal effect. So product B causes lower sales of product A. That's something important to bear in mind that we have to revisit several times throughout today. So now you may ask, well, where do we get the information from, the quantities? And for a new product, a yet to be launched product, we have to rely on domain expertise. Somebody is making a forecast about the sales of product B, and so typically we would come up with a distribution with some degree of uncertainty in terms of the sales forecast for the new product B. Furthermore, we would also have to estimate how new product B affects product A. Again, in the absence of any tangible sales data looking forward, we would have to create some estimates. In a Bayesian network, we can enter these estimates in the form of a conditional probability table, and with that fully specify this very simple Bayesian network. Once we have that specified, then we can certainly compute effects. But that's not particularly interesting because any inference with this network would simply play back what we have already entered. So the results of such inference computation would be kind of obvious. So you may say, okay, couldn't we have done that in Excel, for instance? Wouldn't this have been a bit easier? Why do we need the Bayesian network representation? Well, here I need to say, no, we cannot use Excel, even though in this very simple case, it might still just work. One of the key problems is with representing problem domains as a spreadsheet that the inference can only go in one direction. I can infer from sales of product B to sales of product A, but I could not reverse that process. Another problem with spreadsheets is that they are deterministic, whereas we will have to deal with probabilistic relationships, and so on. So for that reason, even though a lot of people use Bayesian or use spreadsheets in this context, they are really not suitable for this particular purpose. Anyway, let's now go forward a decade and a half from our original example and go beyond this very simplistic example with just two vehicles. Now, reality today is quite a bit more complex. And for instance, just for BMW, the portfolio of utility type vehicles includes the X1, the X2, the X3, X4, X5, X6, and soon there will be an X7. And the other day I read about that there is even a an X8 under consideration. So I'm sure they are now debating such substitution cannibalization topics at BMW right now. And given that they have several common attributes, they are all kind of utility, at least somewhat utility-focused vehicles, and I'm including here station wagons and crossovers, etc. We can assume that there indeed is a lot of cannibalization going on. In fact, when I was car shopping last year, I was considering some of these vehicles and really looking at should it be this one or that one. So this is, in a way, cannibalization here is a very realistic assumption. So what about now capturing this as a Bayesian network? When we're saying everything is related to everything else, should we perhaps use a fully connected network? You know, just one node for each model and assume that everything is related. Yes, we could do that, but it would no longer be possible to specify all these relationships with domain or expert assumptions with domain knowledge. So we would require thousands and thousands of parameters to be defined. No expert could potentially do that. So our question now is, can we perhaps machine learn these potential relationships from data? Now, can we apply algorithms to discover these relationships and quantify them? Yes, perhaps we can do that, and that's what we will attempt to do for the rest of the afternoon. Not the afternoon, the rest of this hour, perhaps. Hopefully it won't take that long. So now if we were all in the same room, somebody would probably ask now, well, isn't there an easier way to get to these quantities of interest? Couldn't we perhaps just ask auto buyers about what they're thinking and, you know, through introspection, learn from them how they arrived at a certain purchase? Well, there are indeed a number of sources of understanding cannibalization. And I just want to mention them so we have a motivation for, kind of a justification for doing what we will ultimately do. We could, for instance, look at trade-in patterns. You know, we could look at what old car do people trade in for their new one and then see from what product they're leaving, what they're getting into. Sometimes that's helpful. At other times, the type of products are just entirely not comparable, so it's not really insightful for our product cannibalization question. You may say, well, how about auto buyer surveys? Everybody gets a survey after they buy a car. And indeed, all these auto buyer surveys ask about, excuse me, what was your second choice? What would you have purchased instead had you not bought the car you actually bought? So the counterfactual question is always being asked. Now, the problem with that is that respondents often exaggerate a bit about their counterfactual choice. They usually don't share what they were really thinking, but perhaps what they were wishing to purchase. So it's more of an expression of the wishful thinking. People are putting down a sports car or some other higher priced vehicle compared to what they actually ended up buying. So in that sense, that's of limited value. And then finally, what normally is a very, very good source of information, choice experiments, or I shouldn't say normally, there are a scientifically sound approach to examine preferences and establish priorities among buyers of any products. One of the problems there is those choice experiments are quite expensive to conduct. And then the problem is it's quite easy to make a verbal commitment or hypothetical commitment to a vehicle. Those choices are you're not putting any money down. You're just saying, hypothetically, I would buy this versus that. So I just wanted to mention that as to why we are going down a different path and we are looking at actual sales data. So we said we want to learn and estimate cannibalization from sales data. But you may say, hold on a minute, you know, because if you remember some previous webinars, I kept emphasizing with machine learned models, you cannot do causal inference. And at the beginning of this webinar, I said, cannibalization is a causal question. We're talking about a causal effect. So let's explore that a little bit. I think this is important to clarify. I'm bringing up our map of analytic modeling and reasoning, and many of you will have seen that several times throughout previous webinars and seminars. And what this map shows is on the x-axis, model purpose, which shows us that models can range in their purpose from association and correlation on the left to causation on the right. In the y-axis represents the model source, and there we have two principal sources at the top, data. At the bottom end of this axis, we have theory. And I would argue machine learning belongs into the upper left quadrant of this map. Quite plausible, perhaps, because machine learning clearly is based on data, so it belongs up there. What is quite important to point out is how far machine learning can reach. And I keep saying, throughout our book, throughout previous webinars and seminars, that with machine learning, really, or rather from machine learned models, or with machine learned models, we cannot enter the space of causation. What we have over there to the right, to the right of this map, we cannot utilize machine learned models for. The inference that we can perform with machine learned models is limited to predictive inference, to association and correlation. And as I said, cannibalization is a causal question that belongs to the right. So now what? What do we do with this? Well, there's one way how we can overcome that, and that is by introducing theoretic knowledge. We will see soon what exactly that is, but that is really the logic behind what we're doing today. We will utilize machine learning for what it's worth, but then we need to introduce our own theoretical domain knowledge in order to be able to answer our causal question. Now, and you probably expected this, Bayesian networks are ideally suited for that because the Bayesian networks cover this entire spectrum. We can machine learn Bayesian networks from data on the one hand. On the other hand, we can also introduce our own theoretical domain knowledge into them. So they're really very practical in this regard. And on that basis, we now want to proceed to our somewhat fictional case study. So let's look at what we're trying to calculate today. So I've narrowed down the field of vehicles that we want to examine. So we went from a dozen to just 4, just to keep things simple and easy to explain. And here I'm sticking to the field of cars, and you should really consider this as a generic example. We could just as well look at washing machines or coffee makers. But since our audience today is mostly male, and I think males can typically better relate to automobiles than household appliances, myself included. So we'll stick to some nice cars. So what we want to know specifically now is, how does product B affect product A, product C, product D? And the way we want to explore that is by looking at sales data, daily sales data of all these products. We want to machine learn a Bayesian network model that captures the joint probability distribution of all these data points over time. How do we do that? Well, that's where BayesiaLab, our software, comes in. Because we want to use that to, first of all, import the data, learn the model, then perhaps perform a few analysis steps, validation measures, etc. And ultimately, we want to get to simulating with this model and finding the optimal policy, all remaining in the framework of BayesiaLab. So at this point, I will just quickly pause my presentation and switch over to BayesiaLab. All right, I think you should now all be able to see BayesiaLab. I've just opened up the software and we see the blue background. At this point, I will open up our data set, our data source. It's a, excuse me, a relatively small file, so I'll import it from a text file. Very simple structure, just 4 columns, 1 each for A, B, C, D. Each row represents 1 day of sales. So I click through the data import wizard. This is all very straightforward. We have all continuous variables. The next step is about missing values, which we don't have, any. So that's quite simple. We don't need to think about that. The next step, however, is important. We need to discretize our numerical values, our continuous variables. So let's perhaps just briefly illustrate that. I'm bringing up the cumulative distribution of the variable B. B, that's the product that we consider to cause the cannibalization of all the other products. So this is what we now need to discretize. If we had certain domain knowledge, we could manually introduce any thresholds. I don't have any particular assumptions in this regard, so I will ask BayesiaLab to automatically discretize all of our 4 variables. I will ask BayesiaLab to use the R-squared genetic optimization algorithm with 5 bins, and additionally, I will ask BayesiaLab to also isolate 0 values into their own bin. So that's what I'm doing. Let me run that. That was quite easy. Here is our initially unconnected network. All right, so perhaps just quick as a sanity check. Here we have the distributions of our 4 variables. Let me just make that larger so you can see it properly. And again, these are all daily values. So distributions, and at the top of the monitors, we see the mean value, that's the expected value. So for product A, the average daily sales is 7.87, and so on. Okay, so now we said we want to learn the relationship between these variables, or rather we want to learn a network that represents the joint probability distribution of all the sales data. So, okay, I think we're now ready to go, and I will go into the learning menu, but first let me go back to the modeling mode. Let me go to learning, and here I will choose unsupervised learning, because we don't have any particular target. Rather, we want to see how all these variables relate to each other, how the sales of these 4 vehicles affect each other. So I And for that purpose, I am going to use the EQ learning algorithm. Now, if I had a lot more variables, if I were examining dozens and dozens of vehicles, then perhaps I would start a little bit more carefully, because some of these learning algorithms can be quite demanding in terms of what they require in computing resources. Okay, so here is our model, and we could now spend quite a bit of time in validating, is this a good model? Does this fit well? What is the out of sample performance? And so on. But we are skipping that part because we have extensively covered those topics in several other webinars. So rather, I now want to think about how we can now use this model for causal inference. We want to know, how does product B affect A, C, and D? That's what we want to find out. But as you look at this model here, you see that the arcs, at least 2 of the 3 arcs that are linked to node B, are inbound. So if you look at this from a causal perspective, this is counterintuitive. Because after all, what we're trying to figure out is, how does node B affect A, C, and D? So here it seems like we're kind of stuck, and that goes back to the issue that we had in the first place. How can we perform causal inference from a machine learned model? Here we have a machine learned model, and there is no obvious path to perform causal inference with this, because the structure as we see it here is non-causal for our purposes. So what do we do? Let me switch back to PowerPoint. So here we are. We have our network. Our arc directions are counterintuitive. So how can we now use this network to calculate the causal effect of B on A, C, and D? Now, there has been a discovery not too long ago, and the discovery was about the disjunctive cause criterion. And this turns out to be very, very powerful, because this tells us how we can perform causal inference with a non-causal model, with a machine learned model, as long as we have correctly identified the confounders. And what is attractive about this criterion is how simple it is. This is really the core of the criterion. It says we propose that control be made for any pre-treatment covariate that is either a cause of treatment or of the outcome, or both. So let's unravel that a little bit. With treatment, in our case, we're talking about the cannibalizing product. That's our cause, the cause that affects the other variables. The outcome, in our case, is the cannibalized product, kind of on the receiving end, the effect. And then what they are talking about in terms of making control for, the covariate that they want to control for or condition on. This is what we would consider confounder in our Bayesian network framework in BayesiaLab. So the way this will work is that with BayesiaLab, or the way this is implemented in BayesiaLab, is that when we perform what we call direct effects analysis, BayesiaLab automatically performs likelihood matching on all the designated confounders. And with that, if we do that, then the computed effect we can interpret as the causal effect. In our particular case, that will be the cannibalization rate. And this is really, really cool, because now we can take our machine learned model. We merely need to identify what are the confounders. Then we can perform direct effects analysis. And there we have our cannibalization rate. If this sounds too nice to be true, yes, there is a catch, and that is we need to furthermore assume that there are no unobserved confounders. So we can't have any lurking variables that are also causes of all the variables in our network. Now that's a very strong assumption, and there is no way to test for that. So we can only accept this assumption or defend this assumption on purely theoretical grounds. So that's one thing we need to bear in mind whenever we report any results from such an analysis. This is what we need to point out. This is our assumptions. So this is how this now all fits together. So we start with machine learning, and then based on our theoretical knowledge, we determine what the confounders are. So that's our theoretical input, our domain knowledge input, and with that we can proceed to performing our causal inference. We can answer the causal question at hand. So we need that theoretical knowledge in addition to the machine learned knowledge. So let me once again switch back to BayesiaLab. Actually, yes, I think you should see the application now. Okay, good. So here we are again. This is our original network, or the network that we machine learned, and we now want to perform inference with it. So the disjunctive cause criterion says we need to control for all confounders. So we need to think about what confounders are, or rather we need to distinguish between confounders and non-confounders. Now, what makes this very simple here, that by default, all variables in BayesiaLab belong to the class confounder. So rather I would have to do the reverse and formally exclude variables and declare a variable formally as a non-confounder. If I don't do that, all variables will be in the network will automatically be conditioned on through likelihood matching. So perhaps this will become clearer when we talk about a specific inference task. As our first task, we will define product A as the target, and we want to compute the effect of B on A. In this case, we would wish to treat C and D as confounders. By default, BayesiaLab automatically treats them as such. And so as we prompt BayesiaLab to compute the direct effect under analysis, report, target, direct effects on target, by virtue of activating this, BayesiaLab automatically performs likelihood matching on nodes C and D. So what we obtain here as the direct effect, that is the exclusive direct effect of node B on node A. So that's our first part of the analysis. So now we want to repeat that for node C. So we want to see how B affects C, and in this case, A and D would be our confounders to be matched on. BayesiaLab again does this automatically. Let me start the target direct effects analysis again. So here we have an effect of minus 0.41, meaning that 1 unit more of B would reduce the volume of C by 0.4, by almost 0.4 units. So then finally, let's do that for node D. Let's see how B affects D. Let's run the same analysis again. Hold on, target, direct effects on target. And it seems here the effect is slightly smaller. Here we only have a unit effect of minus 0.24. So, but overall, I would say these are fairly strong effects. So one more unit of B really seems to have quite a significant impact on the other variables, which leads us to the question, is it good to have B in the portfolio? Would we perhaps be better off not having that product at all? Let's ditch it. And those decisions have to be made all the time when you look at car portfolios. But in order to come to a decision, we can't just look at volumes by themselves, but we need to think about the utilities that are associated with it, or rather costs and potential profit. So how are we going to do this here? Well, first of all, I will change our model as we have it. So I'm starting with the machine learned model, but I'm now going to modify it. I will ditch the data from which we have learned this model. Or not quite yet. First, I will go into this model. And here we're lucky because the way we have learned this model, the EQ learning algorithm, actually yielded a lot of equivalent models. And so within that class of equivalent models, I can change arc directions. Now you may say, couldn't we have done that sooner? Yes, we could, but then we couldn't have illustrated the likelihood matching approach. So now within this equivalence class, I've changed the arc directions, and now I'm going to introduce a decision node. Hold on, I didn't want to introduce two, I only want one. And this decision node I call product policy. This will be a node. Let me perhaps just move this a little further to the center of the screen, so we have space for everything. This product, or rather this product policy, we will use, first of all, let me define the product policies. I will call the product policy no B, and B standing for let's ditch product B as opposed to let's keep product B. And then I will connect this product policy to our node B. Given that I'm adding a parent node, the yellow warning triangle comes up that tells me, hold on, something is now missing. And that refers to the probability distribution. And here it's quite simple to fill this out, because for policy B, we would assume that everything stays the same. For policy B, we would have the sales distribution as it was, as we have actually observed it. For the policy no B, however, we would expect that sales would be zero. So zero sales would have 100% probability, and anything above zero would have to have a zero probability. With that, we have now once again fully specified this network. But as I said earlier, to really evaluate whether something is a sound business decision, we really need to take into account costs and profitability. For that, we can use BayesiaLab's utility nodes. And I will now create utility nodes, one each for each node, or for each product. So I'll link A to the utility node UA. And now I'm going to make up values. I will create formulas that tell me the value of each unit sold to the company. And here I'm totally making up values. For instance, here I will say for each unit of A sold, we're perhaps making $1,000 gross profit. So I'll validate that and then close that. So that utility node will represent the value, the profit to the company provided by each unit of A. Let me repeat that for B. I'll call that UB. Product B is a slightly bigger car, so perhaps we can say our profit is slightly more. Let's say we have a $1,500 gross profit. Then for product C, we rename that. Let's go up quite a bit. Here I'm saying, you know, we're now getting into bigger SUVs. I will say we'll make a $4,000 profit on that vehicle. And then finally, product D, that's the biggest of all of them. Here we're making a $5,000 profit. Okay, so now we have fully specified that. I can now switch into the validation mode. We see all the monitors for our 4 products. I will add monitors for our 4 utilities. And finally, a monitor for product policy. So this now allows us to compare the 2 product policies. It's as simple as choosing either one by clicking. I'll start perhaps with product policy B. That's what we had. That's where we started. And so for this product policy, we would have a gross profit each day of $92,800. If we now switch to policy no B, we would have 98,300. So yeah, so with policy B, or rather with policy no B, we would have a slightly higher utility in total as opposed to doing product policy B. So it seems like actually quite a bit more. Sorry, 98,000 versus roughly 93,000. So actually no B seems to be quite a bit more profitable than no B is much more profitable than B. Let me just fix something here. I forgot to correctly label the utility for D. But perhaps if we're now proposing to X product B, perhaps the product manager may say, hold on, you know what, there is potential in this product still. We can cut cost and get our profitability up. So let me now explore the scenario. Now I'm changing the utility, the gross profit for B from $1,500 to $3,000. And now we can examine that again and compare our scenarios. And now, lo and behold, the policy that includes B, product policy B, now yields a gross profit of $100,000 even, as opposed to a gross profit of $98,300. So in this case, now the product policy B would be the better policy as opposed to not having B. Here, in this very simple scenario, we can simply click through our options. Sometimes we have more than just one policy. We could examine all these products simultaneously. And for that purpose, we can automate that search for the optimal policy. With BayesiaLab, we do that. Let me just remove that real quick. We can do that through the function learn static policy. We saw that in the previous webinar where we're looking for the optimal health policy. Now we're looking for the best profitability. Let me just run this here. I left all the parameters the same. I'll now simply ask BayesiaLab to search for the best policy. I get the response in the form of the color of our decision node, of the bars in our decision node. Given all our inputs, now the best policy would be to have B. But if I were to change it back to $1,500, actually, let me just do that, just to be complete. Let me now, I've now lowered the utility of product B. Let me search for the new static policy again, and you'll see that now no B is highlighted. So that is now the much better choice. Again, if you only have two options, it's simple enough to click your way through and just try everything. But most often you wouldn't just consider one product, but a multitude of products, and perhaps try out dozens, if not hundreds, of possible scenarios. And you wish then to examine which of these might be the most profitable one. Okay, and what I've done here in a highly simplistic form, these are the real questions that product managers, brand managers face. But one of the key elements that I've often seen as missing is formally capturing the cannibalization effect, which we have very explicitly now encoded here. That is now part of our reasoning. We can reason actively with the cannibalization rate as opposed to dealing with it like as this mysterious fudge factor that kind of darkens all prospects, all business opportunities a little bit, but in a somewhat, in a somewhat mysterious way. Here we've now explicitly captured it. We can debate it. We can enter our assumptions. We can learn it from data and then actively work with it. So let me switch back into PowerPoint. Our seminar will continue, or rather I should say our webinar series will continue, just not next Friday. Our offices will be closed on March 30th in observance of Good Friday, but then on April 6th, April 13th, our webinar will continue. We have not yet finalized our webinar topics. One of the things that are pending is dynamic Bayesian network models. We know that that is of great interest to many, so that will sooner or later get added to our webinar schedule. Also, what I should say is if you have any particular topics that you find interesting, please feel free to email us to suggest future program items. We'll gladly consider those. So with that, I would encourage you to take a look at our website to check out our upcoming event schedule beyond our webinars. Of course, we have our course schedule that is listed on our website. I would like to encourage you to share some of your thoughts, your questions on our user forum under bayesian.com/community. We have very lively debates there on BayesiaLab functions, applications, etc. And then, of course, what you've seen today, you can immediately replicate with a trial version of BayesiaLab. In fact, what you saw today, for those fairly simple examples, the basic demo version is just fine. So you can watch the webinar and in parallel build your own model and arrive at the same conclusions. So I had already referenced our professional courses. Our next one is in Sydney, Australia. That starts on April 11th. Then the program continues in Seattle, Boston, and San Francisco. San Francisco, I should emphasize, because that course was rescheduled from March to July. So if you were considering the March course in San Francisco, that will now be hosted in July. And then, of course, please do put our annual BayesiaLab conference onto your calendar. We have a great venue right off Michigan Avenue near the John Hancock Tower. It should be a great opportunity to meet fellow BayesiaLab users. We expect to have researchers join us from all over the world. So I think that should be a fantastic event. So with that, I would like to thank you for your time and interest this afternoon. I hope the presentation was useful. I look forward to seeing you again at one of our future webinars. And in the meantime, once again, thank you and have a great weekend.